Thank you very much for being here, everyone, and a tremendous thanks to SLA for hosting this. Frank, thank you. And Dr. Shaw for arranging, Charlie and Chris. What I'd like to talk about today is some data that we collected in 2018 and in a resulting paper that we put out in July of 24. See if I can do this right here. Okay, so this project started, my understanding is that toxic cyanobacteria blooms came back to or initiated in Skaneateles Lake in 2017. And we were working at Lake George with this, with kind of this new research paradigm, merging high-frequency sensors and computer modeling, specifically of high-resolution weather circulation. And we were directed, in quotes, to we were very much appreciated it, to come to Skaneateles Lake to hopefully provide some insights into what was generating the blooms. So we came and primarily, again, high-frequency sensors and computer modeling. That vertical profiler in the upper right there, that was the only sensor package that we had on the lake. And I want to point out to you, in that picture, there's some white streaks on the surface of the lake, and that's indicative of Langmuir circulation, which I'll talk about in a few minutes. This was the paper that came out of this effort, and highly recommend it. It's a long read, so grab a beer or a bottle of wine, and any questions you have that I can't answer, we obviously we can go back to the paper. As we go through this, I want to point out that the location of the vertical profiler, again, all of our sensors, were where that green dot is. And I believe that's pretty much in the vicinity of the water intake for the city of Syracuse. And that's actually why we were there. I didn't know that immediately at the time, but I understood that pretty quickly. And you'll notice that the positioning is in this upsloping trench, exactly what Chris was just showing us earlier. And it's, we'll see that it's in kind of this wash zone of the thermocline. So I used to start at the beginning and end at the end, but everybody was asleep by that point. So now I start at the end, and then I work my way back a little bit. The crux of what we found, again, this is largely from the measurement data, but it was substantiated with our modeling data, was there was a three-step sequence that preceded every HAB on Skaneateles Lake in 2018. And there were a total of 8 confirmed HABs in that year. We deployed right at the end of July, and we were on the lake until the end of October. And the 8 HABs, they started right away after we showed up, which we caught a little flack from. But the first 3 were August 4th, 5th, and 7th, and then the last one I think was October 9th or 10th. But what we found was that they were all preceded by a disturbance of the lake bed by the thermocline, and I'll get into a little bit more detail on that in just a minute. And that then was followed by this vertical circulation within the water column. And that circulated, we believe, nutrients and cyanobacteria, basically on a conveyor belt through the water column. And both the thermocline raking the lake bed and the vertical mixing in the column were very, very wind dependent. The third step was the wind calming. And this is what everybody always associates with a precursor to a HAB is, well, things got very calm. And that's true, and that allows the buoyancy of the cyanobacteria to allow it to surface. So I'm talking about the thermocline raking the lake bed and then this vertical circulation. So just as a little refresher here, the thermocline rakes the lake bed as a result of internal waves. So that's a wave literally in the thermal structure of the lake. So you have warm epilimnitic water during the summertime, cold hypolimnitic water, and that boundary, which we're seeing as these lines in this diagram on the left, the line in the middle of the lake. That's the thermocline, and the wind deflects that, and when the wind stops, that can oscillate back and forth. And in extreme conditions, and in conditions that I think are very dependent on the depth of the stratification, this rocking back and forth, which is called an internal seiche, basically a standing wave, that can manifest as a progressive wave. So instead of the thermocline just rocking back and forth, raking the lake bed, it can turn into a singular wave or wave train with about an order of magnitude more energy when it shoals than does the internal seiche. So that's why we're talking about this raking of the lake bed. And it's in this area that Chris was talking about, this wash zone. Now on the right is Langmuir circulation. This is when you see the bubble streaks on the surface of the lake, more or less parallel with the wind. You're looking at the confluence of these helical coils of flow in the water column. That's Langmuir circulation. So this is data from the Brannan, Scholes, and Driscoll study that Chris was talking about, where as you go deeper in the lake, the phosphorus content in the sediment increases. And that gray zone there is roughly what we calculated to be the wash zone of the thermocline raking the lake bed. So that's the depth region of concern, at least during our deployment in 2018. And we saw from Brannan et al. In 2023 that where our vertical profiler was, we were in a vicinity of something like 900 to 1200 ppm. So we were over a lake bed area that was very high in phosphorus concentration. This is data from early August. The top is wind speed and direction, time left to right. The heavy black bars are day delineations. The middle panel is a temperature profile, and the bottom panel is turbidity. And what the middle panel is showing us, and this is after, it starts on August 4th. This is after, on August 1st, I think it was, there was a 20-mile-an-hour wind out of the south for about the whole day. And so for that whole day, that wind was blowing the warm epilimnetic water northward, and it was deflecting the thermocline. And when that wind stopped on August 2nd, the thermocline started to oscillate back and forth. And so what we see in the temperature profile is this upwelling of the cold and blue in it's cold hypolimnetic water. Because of the geometry of Skaneateles Lake, the frequency of that is roughly every day. And this goes back to Marion's formula from the 1800s. The geometry of the lake basically makes it a clock, a one-day clock. It's just short of one day, but more or less every day that cold hypolimnetic water was upwelling, and then it was receding. With each upwelling, we see the turbidity at the lake bed bloom up. Now this is blooming up about 3 or 4 meters. So almost the height of this room. So the thermocline is raking the lake bed. It's causing this plume of turbidity off of the lake bed that we know is very high in phosphorus concentration. We also saw this this is ADCP data. It's the depth of the lake on the y-axis, time left to right. And what we're seeing, this is north-south velocity. We're seeing the receding of the water at the lake bed, and then the immediate progression of it. And this suggests that our vertical profiler was deployed right at the south end of the wash zone as it existed for this time. So this is really the best example that we have of this three-step mechanism. We see at the two B's up there, we see internal waves coming through, that cold hypolimnitic water coming up. And at B prime, down at the second to bottom panel, so let me restart. Top panel is wind speed and direction. The second panel down is temperature profile. The third panel down is north-south velocity, I think. Fourth panel down is acoustic backscatter from the ADCP. And then we have turbidity, and then we have vertical velocity here on the bottom. So at B prime, we see the upwelling of the hypolimnion, both in the temperature and in the turbidity. But what happens is, if there's nothing to pull it upwards through the column, it just settles back down. So not every internal wave causes a bloom on Skaneateles Lake. What we see at F, the wind increases, and we start to see some Langmuir circulation going from D to D prime. Now you can see that in the vertical velocity. That's those helical coils. And as they transit the vertical profiler, you see the lake water literally going up and down below your feet on the profiler. You don't really see that, but the instrument sees that. And we see at F, there's an intersection between the pluming lake bed, that turbidity, and the vertical mixing from the Langmuir circulation. And F is the magic. That's the magic, because that, subsequent to that, we start to see an increase in turbidity in the water column. So that's the mechanism I described with that first graphic. Now there's another mechanism that we describe in the paper as a shortcut. Now, what happens is when the wind from the south blows northward and it deflects the thermocline downward at the north end of the lake, it's setting up for an internal wave, but sometimes the wind can hold it there for a long period of time, hours to a day. The Langmuir circulation can go all the way to the lake bed, and that's called Langmuir supercells. We see that at I, and that's due to the wind increase up at G. So the wind increases at G. At H, it pushes that thermocline down. So we see the lake column, the column go isothermal at H. And if we trace down to I, we see the vertical mixing going all the way to the lake bed. And then subsequent to that, in the turbidity, we see the column getting very turbid. Now I want to zoom in here. So this is the same image, only I zoomed in, particularly with the acoustic backscatter, which is the fourth panel down. We still have the Langmuir supercells at D, and up at E, you can actually see from the backscatter, you can see lake bed material being entrained up. This isn't the first time this has been observed. This was really observed initially, I think, by Anne Gargette off the coast of New Jersey in about 2007, in, ironically, about the same depth of water. So we have these two mechanisms. Now, let's see if I can go back here. This is the previous diagram. I call this a week in the life of a HAB on Skaneateles Lake. This is 7 days. That last day, there's a couple of red dots in the middle of some of those panels. That was a confirmed HAB day. And you can see also in the backscatter, there's quite bright backscatter near the surface, and we believe that to be reflection, acoustic reflection, off of the aggregating cyanobacteria near the surface. So I included this because for years I've been talking about this kind of the shortcut mechanism. I finally put a diagram together. And this dovetails with what Chris was just describing. This is a crude depiction, by the way, of the north end of Skaneateles Lake. This kind of shallow 7-8 meter plateau at the north end, and then the deepening, which is this trench that we were over. When there's light to moderate wind, you can get Langmuir circulation, which is those vertical ovals that we have with the arrows on them. And at the north end of the lake, where it's only 7 or 8 meters, you can have Langmuir supercells. They probably happen all year long when it's breezy from the south. But the problem with it not creating a HAB every time that happens gets back to Chris's data and Charlie's data with the reduced level of phosphorus in that sediment in the shallower areas. But when that thermocline gets deflected, the way I have in the bottom panel, well, all of a sudden, that red depiction of Langmuir circulation, that's a new set of Langmuir supercells that now are penetrating to the lake bed in an area that we know has elevated phosphorus content. This is 2 images from our hydrodynamic modeling, and this just shows the top panel is more or less with the thermocline at rest. The way this is that the lake surface is kind of shown at an angle at the top with wind vectors. The tan-colored area is the epilimnion. The dark stripe is a 16-degree isotherm representing the thermocline. And then the gray area is hypolimnetic water. And in the top graphic, we see basically a fairly relaxed thermocline. And in the bottom graphic, we see the deflection of, right here, deflection of the thermocline. And if anybody wants, I have some really great animations. I think I showed them back in 2020. This afternoon, we can certainly take a look at those animations, and it shows the dynamics going on in the thermocline, both during Seiche events, i.e. kind of that rocking back and forth, and also progressive waves. So from that, we developed 2 predictive mechanisms, 2 predictive algorithms. This is basically only using 3 metrics. One is turbidity near the lake bed, the bottom 3.5 meters. The vertical velocity near the lake bed, again, bottom 3.5 meters. And then surface winds. So these represent the 3 main drivers that I talked about in that 3-step sequence. And using empirically derived thresholds, we come up with this model. Now on the bottom, the gray bars indicate confirmed days with blooms, DEC confirmed. And the green dots are predictions based on this model. We do over-predict, but we're convinced that the lake was very likely set up for a surface bloom. It just never manifested as a surface aggregation. We also, now this is not in the paper, but we also looked at another mechanism to predict blooms. And here we're looking at, again, wind speed and direction, acoustic backscatter. I'll mention the 3rd panel in a minute. This has vertical velocity, and on the bottom is a summation of vertical velocity through the column. That 3rd panel up from the bottom is looking at the variance of acoustic backscatter in the top 13 meters. The blue line is the instantaneous variance. The light blue line is a 1-day moving average, and the dark blue line is a 3-day moving average. And we noticed that when the 1-day moving average went above the 3-day moving average, it was indicative. Again, the red dots in the next panel below are confirmed HAB days. So we call this the HABs cross. And what's going on here is we're only using acoustic backscatter. And we're saying, okay, well, when the variance is low, the backscatter produced by the cyanobacteria indicates that it's relatively distributed within a column. When the variance increases relative to the time leading up to then, it's very likely the cyanobacteria is starting to aggregate towards the surface. So we hit all 4. We over-predicted on that second to last one, and we think that's because the lake was set up, but then there was sufficient wind to draw the cyanobacteria down into the water. By the way, in 2018, the cyanobacteria, it was there the whole time. This is, on the top is phycocyanin, instantaneous 0.5 meter down and 1 meter down. And then on the bottom is phycocyanin summed through, I think, the whole column. And I'll just mention on the bottom there, we can see that there's cyanobacteria in the column all season long. The red dots, again, are confirmed HABs days. I'll get back to the top in a minute, but one thing that's interesting on the bottom is that the first 3 HABs in August 4th, 5th, and 7th, they were during a relatively light region or area of time relative to the concentration of cyanobacteria in the column. So you don't need a lot in the lake in order to produce a surface aggregation. On the top is a detection mechanism that we developed, where again we're looking at 24-hour moving averages compared to the instantaneous. And it's a very simple algorithm. It's basically, well, when is the instantaneous some percentage above the 24-hour moving average? And I forget, something like 70% with one and 60% with the other. It's in the paper. But you can see we're detecting very closely all of the blooms that were confirmed. Now, I want to point out, if you remember where the vertical profiler was, it was essentially out in the middle of the lake off of Mile Point, so it wasn't in the middle of the lake, but it was halfway across the lake. And the confirmed blooms were scattered around the north end with 1 or 2 at the south end. And yet, out in the middle of the lake, we were still able to detect those blooms, even though they were confirmed on the shoreline. And the real takeaway for me there is that the blooms are not really localized. They're still being generated probably along this wash zone, out in the middle of the lake. And then they're just drifting in and out. And again, that cyanobacteria, it's in the lake. And what we call a bloom is nothing more than a surface aggregation that may or may not produce toxins. So, getting towards the end here, if anybody wants to try this at home, I keep harping on the vertical mixing, the Langmuir circulation. I think it's critical here. And that profiler in the upper left, that's on Skaneateles Lake. That's our Atlantis custom-built RPI and IBM in 2018. Again, you can see those white streaks. This was July 31st. I think it was a Tuesday. And that machine is what allowed us to create this beautiful ADCP data. But what we have found since then, we built a couple of new vertical profilers, and one of them is shown in the lower right there. The new profilers are bigger, and they have way bigger pontoons. Sounds great, except for those new profilers ride the waves. Now, when you really want to know about vertical mixing, it's when it's windy. And when it's windy, there's a lot of waves. And when there's a lot of waves, we find that the new profilers, they're so buoyant that they really heave quite a bit. And I'm having a very difficult time to generate this quality of data with these new profilers. There's just too much buoyancy to it. And so we're looking at ways to change the ping rate, which I'm almost maxed out with that, but also to kind of somehow put a shock absorber on the ADCPs. Now, I usually run long. How much time do I have, Steve? Because okay, I have some backup slides. I'll just go through these quickly. This is some bathymetric work that we're doing at Chautauqua Lake, which has been very helpful to identify this wash zone that Chris was talking about. This gets back to something Chris was mentioning. There's this constant thinking that, well, there's no internal loading going on in a lot of the Finger Lakes. In fact, this is the action plan for Skaneateles, and it says we don't think there's any internal loading. Well, I think I think we know better at this point. So that's that. Another point I want to make, what the wind giveth, the wind taketh away. the wind and the calm wind generates these blooms, we think, and then it takes very little wind to generate a small vertical mixing at the surface to basically suck that bloom back down into the column. And the one thing I'll leave you with, so when we showed up on the July 30th of 2018, I spent most of the time deploying the vertical profiler and the rest of the time looking down into the water column in complete amazement of how clear it was. I mean, everybody had talked about how clear Skaneateles is, and I'm like, wow, they weren't kidding. Well, I had to come back on that Friday after this big wind event, but the day before the bloom, the first bloom on August 4th. And see if I can, go back there. So that Friday, this is from the vertical profiler. I'm looking down, I'm seeing all this particulate. I kicked myself for not having filled a water bottle and looked at it under a microscope, but I didn't. My guess is that these are colonies of microcystis developing in the column, and this was the day before. It was extremely calm on the 4th, and then those colonies rose to the surface. And in fact, I got a call that day when I was out on the VP. A couple came up to me in a whaler, and they said, "Oh, this is great, blah, blah, blah," and I gave them a card. Well, they called me the next day, and they said, "Hey, we got stuff coming up on the surface. You guys know about this?" And I'm like, well, that was the start of us hopefully figuring out the problem. So let me go back because I need to leave it on. This. So I consider myself, I'm really the messenger. There was so much effort and work put behind this by a whole lot of people. I just feel lucky that I was part of, helping to figure some of this out, and that I get to come and talk about it to great people like you. Thank you very much.
Mark, that was a fascinating talk. Thank you. I'm Rick Smith, Global Aquatic Research. I was super interested in this because we see this often when you have HAB reports in shallow areas. We're out in the middle of the lake and we basically see them in various streams and pools kind of, occupying some percentage of the lake.
Yeah.
And something I know that came from John Halfman's work with FLI, they talk a lot about this nearshore loading of nutrients. And something they talk a lot about is macrophyte breakdown. So this is really interesting because this is probably a higher quantity of phosphorus overall, because you're talking about all the nearshore, basically these hot zone type areas, right, where you get deep enough that you have high concentrations of phosphorus in the sediment, but shallow enough that you can basically get these Langmuir supercells actually hitting the bottom, right?
Yeah.
If you look towards any kind of mass balance, is that possible to get from your data, where we can actually look at TSS, concentration of phosphorus, and then actually look at phosphorus requirements of the microcystis and get some estimates of biomass in the water column to see what percentage of their total phosphorus requirement, basically?
Yeah, I would say not from the data that we have. I think that would require an extension of the hydrodynamic model to really model it basin-wide. Because as much as I'm describing it as being kind of this homogeneous issue at the north end, there really is a lot of heterogeneity throughout the basin. So I think that's possible, not with the data that we have, but I think, building on that probably would be helpful. I want to bring up one other point. I mentioned when I showed the confirmed HABs, there was on September 13th and 16th, I think, there were blooms reported at the south end. Or near the south end, or actually about halfway up the lake. And that is kind of inconsistent with this model that I'm showing here. But what happened prior to that HAB event was a very energetic progressive wave. So what happened was the wind was very strong and it blew towards the north, and I believe the stratification had deepened. it deflected the thermocline, and when the wind stopped, there was such a mass of warm epilymnitic water that when it flowed back to even out, it actually depresses the south end, and this is textbook. It depresses the south end, and then that becomes a progressive wave. So it doesn't do this. It deflects so much that all the energy starts at the south end, comes up the north. And it's a depressive progressive wave, meaning it kind of, there's this V shape to it. And because it's deeper and it's higher energy, it starts to nail all of the shelves up along the side of the lake. And that's when we saw this widespread bloom. And I'm happy to show you the animation, because we have that in our animation, of this progressive wave coming up and hammering all the shoreline and then breaking at the north end. And this is another interesting point, and it complicates things. The progressive waves, if you look at the standing wave, it's like this, and you can calculate that wash zone. That when those progressive waves come and they have that depressive V or U to them, they shoal much further south than the Seiche wave interacts with the sediment, but with much higher energy. So we didn't see those directly other than in our model, but we saw in our measurement data the after effects of this thing shoaling in the shallower, or in the deeper water. So it's shoaling in the deeper water in a whole different wash zone, if you will, or at least an extension of the wash zone. So I know that's not answering your question, but it is really kind of an interesting, a complicating factor of the whole thing. So on the one hand, I'm painting this as a simple picture, but as we all know, nothing's really simple.
No, thanks, Mark. That actually answered my second question. Are all these zones in play around the lake, or just the north and south end?
Yeah, no, and this is where Chris's bathymetry really is going to be super valuable. And because I think that, if we can continue on with any of this modeling, we can start to see how that thermocline is transitioning around the lake and what areas of the lake bed are being impacted by it.
Thank you.
Thank you.
All right, we'll end there. Definitely time for discussion.
Great. Thank you very much.